So this first problem is on inverse variation, and remember, if you're talking about direct variation, like lines, that's direct variation. But when you talk about inverse variation, it's not y equals constant times your independent variable. It's y equals some constant divided by your independent variable. So in inverse variation, one will get bigger, one variable gets bigger as the other gets smaller. So this is your model, y equals k over x. And so we're going to substitute into there those values. So the y is -8 equals, we don't know the k, and then we know that the x is 2. Well, we can solve for the k by multiplying by 2 on both sides. And so then we're going to get -16 is equal to k. Now that we know that k is -16, I can write y equals -16 over x, and that is my model for the inverse variation. So given any value of x, I can solve for what value of y is associated with that. For number 2, we don't see the word inversely. So what we do see is that z varies jointly with x and y. So z is proportional to x and y. We just don't know the concept of proportionality yet. So we just substitute these values in. So 2 is the z that we're given. We don't know the concept of proportionality. You can think of this as kind of the slope. And we do know the x, which is 0.2, and we do know the y, which is 3. And then we just simplify this, so we get 2 is equal to k times 0.6, and then divide by 0.6 on both sides, and you solve for your k, and then you can rewrite. And k is equal to 3.3 repeating, but just because I don't like repeating decimals, there's nothing wrong with it if you put the repeating decimal, but I want to be exact, so I'm going to use improper fraction. So you can write it as y equals, the value of k is 10/3 times, and it varies with x and y, and actually it's z. Z varies jointly with that, so it's this. You could use, I would definitely accept this answer as long as you put the bar over. This is great. It's correct. The problem is it's hard to enter this into the calculator. You can't enter repeating decimals. So if you want to replicate actually doing an improper fraction is just better as being able to actually enter it in. For number 3, before I enter the values in, I want to put my model. So z varies, and pretty much anytime you see varies, that's kind of the equal sign if you've noticed the pattern so far. So z is equal to, and then we have all that information. So I'm going to start with z varies, and they say it's directly with x. So that means that I know that the x is going to go on top directly. It's going to be the part of the numerator. Now inversely with the product of r squared and y. So these are inversely. Inversely means it goes on the bottom, and that means r squared and y are going to be multiplied together on the bottom. And because it varies, that means that you could have a proportion, so you put your constant of proportionality. So now I'm going to plug in my numbers. Z is 1/2. K, I don't know. I'm going to solve for. X is 1/3. And Y is 1/5. I put 1/5 second. And then R squared is the 3 squared. Then we just simplify and we solve for K. So to cancel out the 1/3, I multiply by 3 to cancel out the 1/5, but the 1/5's on the bottom. I really multiply by 5 on the denominator, which is kind of like dividing by 5. And then to cancel out the 3 squared, I multiply by 9 on the top. So then I just do that same thing to the left. So I'll just punch all that in here, and so I get 27/10 for K. And this one's not a repeating decimal, so it doesn't matter if you write 27/10 or you write 2.7. I'll write both answers. I'll accept both answers. So this one's maybe easier to write, but let me show you a better way to write if you use an improper fraction. We don't like fractions and fractions. We'll have some problems later where we deal with complex fractions. So if you use the improper fraction version, you should technically write the 27 as part of the numerator and the 10 as part of the denominator. Now, just to be clear, if you wanted to put the y first and then the r squared second, so say you wanted to put 2.7x over y and then r squared, this is also a perfectly acceptable answer. answer. So there's at least 3 or 4 if I swap the r squared and the y here. There's several different ways to write the correct answer here. For the next ones, we're trying to see if these are inverse or direct variations, and they're possibly neither. And if we can write them, we want to write the model. So the first thing to check is, okay, the x column goes up, the y column goes up. So the first thing I'm thinking is this is probably direct, or at least it's a candidate for direct. Let's see. 3 to 6, to get from 3 to 6, I can multiply by 2. To get from 5 to 8, oh wait, I can't multiply by 2. So direct variation doesn't make sense here. In fact, the relation here isn't multiplication at all. It's actually, it seems to be I could add 3, add 3, add 3. So this is not a direct variation. Now, you can write a linear equation for this, and it would be y equals 1x plus 3. This is a linear relationship, but for direct variation, remember we have the condition that you can't have a y-intercept for them to be very directly, or your y-intercept and specifically has to be 0. So this would actually be neither, even though it's a direct variation. Even though it's a linear relation, to be a direct variation, you need to have y-intercept of 0. This one, I see these are going up, this is going down, so that's probably a candidate. This is probably a candidate for inverse, and I'm not sure if it works out yet, but let's check it. So if it's an inverse, I can write in the form of y equals k over x. 32 is my y, I don't know my k. Let me try an x value of 4, and so solve for k by multiplying by 4 on both sides. And if I do 32 times 4, 128 seems to be the k. Now I need to check if it works out for the other ones. So I can do, I think the k is 128, which would mean my model would be y equals 128 over x. So this is probably the answer, but let's check if it works. There's several ways to check. I could just keep doing this for each of these. So I can do 16, which is my y, equals k over 8. And I can just see that, check and see if 128 works. Or I can go to here and do 16 times 8. And it also comes out to 28. If I do 8 times 16, of course that'll work. If I do 4 times 32, that'll also work. But another way to check is this. You can check by leaning on technology. I can actually enter in 128 over x and then go to my table, and I can modify my table to be able to take to be able to actually ask for the values, and then I can just check that it works. If I put 4 here, oops, I actually should have set that to, actually was set to ask there. So I can try putting 4 here, and look, it maps to 32. If I put an 8, it outputs a 16, or maps to 16. If I input a 16, it outputs an 8. If I input a 32, it outputs a 4. And if I wanted to just guess other numbers, say I carried 10, it would output 12.8. But now you can use this variation to complete infinitely many sets. So it's an inverse variation, and this is the model of the inverse. We're trying to understand asymptotes in numbers 6 and 7. So first, let's understand the asymptotes here. So the standard reciprocal function, or like a rational function with, it's not shifted or anything, 7 over x, usually it's going to be graphed this way. It's going to have an asymptote at y equals 0 and an asymptote at x equals 0. So if I want to have an asymptote at x equals 1, so here's where I want it to have an asymptote. Instead of here, along the x-axis, I want it to have an asymptote at x equal 1. Well, what direction was that asymptote moved? It was moved 1 to the right. How do we shift this thing 1 unit to the right? Well, we put a minus 1 next to the x. Now, again, and then the vertical asymptote is usually on the x-axis, or the line y equals 0. But here, the asymptote, they want it to be at 2. So that's shifted up by 2 units. Well, how do you shift these functions up by 2 units? You just add a 2 on the end. So your answer would be y equals 7 over, you don't have to put parentheses, x minus 1, but you could put parentheses around this if you choose. And then plus 2, this shifts it right 1, this shifts it up 2. Same thing with this one. Again, the parent function, we're using the same parent function. And by the way, this 7 at the top, the numerator has no bearing on the asymptotes at all. Only the 1 and the 2 here. So if you can see how 6 works, it should be really easy to see how number 7 works. So I'm actually going to do the vertical shift first. So if shifting it up 2 would give you this asymptote, then obviously shifting it down 2 would give you this asymptote. And here we have vertical asymptotes. Well, if you did -1 to shift it to the right by 1, then you must do +3 to shift it to the left by 3. And you can confirm these by graphing. And I can write this in function notation too if I wanted to. I could write f of x, but since they did y equals, I'm writing y equals. But these are your answers for 6 and 7. And they do ask you to graph them, and I can graph them on Desmos really cleanly, or I can graph them in my calculator really cleanly. So, but let me show you how I can sketch them just knowing their asymptotes. 1, 2, 3, but that's not where the asymptote is. It's not at +3, it's at 1, 2, 3. It's at -3, so I'm going to write a little dotted line. And then the other asymptote is at -2, so I'm going to write a dotted line. And the graph is just the same shape, these two little curls here. It's the same shape as the standard rational reciprocal function, but it's just in a different place. On your calculator, I can enter that into my y equals. And you can also use this to reverse engineer to find the equation. You can sort of guess and check, or at least confirm your answer. And if I go to, let me just do the standard zoom 6, and I get exactly what I sketched without using a calculator. And if you want to check to see if these are right, you can kind of like look with your finger and say, okay, 1, 2, 3. Hey, yeah, that the vertical asymptote is at -3, and then here the y value seems to be kind of leveling off at 2. Or you can also use your trace function to check all that stuff to make it a little more obvious what the asymptotes are. But as long as you understand how to shift vertically and horizontally, and you understand that the default asymptotes are at y equals 0 and x equals 0, then just knowing how to shift them up, down, left, or right gives you the answers. So here I'm going to find any holes and also any horizontal or vertical asymptotes. So we have a hole anytime you're dividing by 0, but that 0 cancels out. So there won't be any holes in these first two, even though the function is discontinuous at vertical asymptotes and at holes. But the horizontal asymptote here is a little harder. I'll come back to that second. The vertical asymptote is easy. If you divide by 0 and that factor doesn't cancel out, that's when you have a vertical asymptote. So if you set x equal to 1, you divide by 0, so that's how you know that's your vertical asymptote. For your horizontal asymptote, here's the rules you follow. That's where you look at that table. You'll find this table in section 8.3, but the idea is that if the top power is less than the bottom power, then the x-axis is always the asymptote, unless the thing is shifted up and down, like in the previous problem. If the top power is bigger than the bottom power, like the highest power, then you're not going to have a horizontal asymptote. But if they're equal, and that's the situation we have for numbers 7 and 8, what you do is you take the coefficients a and b here, and you divide those. Now the coefficients here, it's hidden, but they're both 1s. So your horizontal asymptote is y equal 1. Don't just write 1, it's y equals 1. But the horizontal asymptote has nothing to do with these numbers right there. It's not 1 because of this, it's 1 because 1 divided by 1. So to give you another example, we have here, we should have a vertical asymptote. We would expect to have a vertical asymptote at x equal -3 because we're dividing by 0 when you said x equal -3. But here's the problem. It's not a vertical asymptote because these factors kind of cancel out. So what really is that instead of having a vertical asymptote, you're going to end up having a hole at exactly x equals 3. And it's going to be, we also call that a removable discontinuity. Now, you will never be able to like really see the holes graphically unless you like go straight to that point and your function will output that's undefined. Just to show you what this function looks like, there's a little horizontal this thing is just levels off because these cancel out. This is effectively y equals 1 is what this equation. And since this is y equals 1, you don't really have asymptotes. Like your line is just the equation, like it's just y equals 1. But you don't see a hole anywhere. You don't see a gap. But if I go to second calc and I go to value, I know the hole is at -3, so I go to value. If I enter -3, I can confirm that I have a hole because at -3, it outputs no y value. Even though I really think that at -3, it's also y equals 1. It should be there. If I go to my table, I can put in, -4, the value's 1. If I put in -3, the value, we get an error. If I put in -2, -1, 0, 1. If I put in 99, you can see that the y value is always 1, except at -3 because there's that pinhole there, also known as a removable discontinuity. And there will also be no horizontal asymptotes here, just as there are no vertical asymptotes, again, because there's a hole instead of a vertical asymptote because the discontinuity canceled out. So for number 10, the easiest thing is to look at the holes or the vertical asymptotes first, and then I'll worry about the horizontal asymptotes later. So first thing I noticed is that, oh hey, these x minus 2's cancel out. So even though I would expect the vertical asymptote at -1 and +2, actually at +2, it's only going to be a hole. So x equals +2 is going to be a hole because these factors cancel out. The x plus 1 factor doesn't cancel out. So if you take x plus 1 and set it equal to 0, you get x equals -1. -1 makes that factor 0. So x equals -1 is your vertical asymptote. You can confirm that by graphing it if you have trouble, if you're not confident doing it algebraically. Horizontal asymptote, well, then we got to go back to that chart. Here's the thing. The power on top, the degree of this thing is 1. The degree on the bottom, there's 2 x's, so the degree here is 2. Anytime your denominator's degree is higher than your numerator's degree, you're going to have a vertical asymptote, horizontal asymptote of y equals 0. So you'll notice this thing will level off along the x-axis if you graph it. Up till now, everything's been factored for us, and that's nice, but sometimes things won't be factored. So in here, I'll actually do the horizontal asymptote first. Notice how the powers are the same. You got an x squared power on top, and you got an x squared power on the bottom, so there's a tie. So the horizontal asymptote is going to be the a over b. In this case, 2 divided by 1. So your horizontal asymptote is going to be y equals 2. Again, you can confirm by graphing. The vertical asymptote is hard to see. It's like, I know it's when you're dividing by 0, but it's hard to see where that is. So if I got to factor this first. The greatest common factor here is x. If I pull an x out, I get x minus 4. So I would expect to maybe have vertical asymptotes at +4 and also at x. But notice how like the x, these x's can kind of cancel out. So instead of having at x equals 0, instead of there being a vertical asymptote, there's just going to be a hole there because they canceled. But there's no x minus 4 factor in the top. So if you set x minus 4 equal to 0, you get x equals 4. So x equals 4 is going to be a vertical asymptote. For number 12, okay, it's an easy function. We don't have to factor it, but notice how it's shifted down by 3. So if you refer to numbers 6 and 7, where we're shifting stuff up and down, that can help here. But for this thing is shifted 2 to the left. So we're going to have a horizontal, we're going to have a vertical asymptote because it shifted 2 to the left at x equals -2. And then normally your horizontal asymptote, since your degree of your bottom is higher than your degree of the top, normally I would think it's y equals 0, but because this is shifted down by 3, it's going to be y equals -3. And in this one, there's no factors that cancel out, so there are no holes in this particular scenario. For number 13, it seems like we might be able to factor this because I see x squared, but this numerator it's not able to be factored at all. It's not a difference of perfect squares. There's nothing to go on. Here's what you should definitely not do. Don't cancel out those 5s. You cannot do that. We talked about that many times in class. So really nothing factors out, nothing cancels out. Also, notice how your numerator's degree is higher than your denominator's degree. So for your horizontal asymptote, there's actually none at all. There's no horizontal asymptotes. For your vertical asymptote, x equal 5 is going to be your vertical asymptote. And since you couldn't factor anything and nothing cancels, for your holes, there's not going to be any holes at all. There's only a vertical asymptote for number. For complex fractions, the key is that we're just dividing. So this is 2 over x. Now I'm going to write this as divided by 1 minus 1 over y. Now this looks really sloppy because we have fractions and fractions. That's why we call them complex fractions. This bottom one is intimidating, but here's the idea. I don't want to have fractions and fractions. So what I'm going to do is get rid of this. I'm going to actually have a common denominator for this bottom fraction. That's one way to tackle this. So instead of writing 1 right here, I'm going to have a common denominator. This 1 is really over 1. Well, what's the common denominator? The common denominator is y. So multiply the top and the bottom by y there. So this is actually y over y instead of writing 1, because y divided by y is 1, whatever value y is. Which it's assumed that x and y can't be 0, since that would make the original expression undefined. So let's first simplify this denominator. This becomes 2 divided by x over y minus 1 all over y. So we're just dividing fractions. So instead of dividing fractions, multiply by the reciprocal. So it's 2 times y over y minus 1. Now I can finally just multiply across. 2 times y is just 2y. And then multiply across here, x times y minus 1. So this is your answer. You could, if you want to distribute, if you choose to do that, you could write x, y minus x. There's nothing wrong with that, but leaving it factored is specifically because it makes the reader see that, hey, nothing can reduce and cancel. So this answer is preferred. I wouldn't mark this wrong. And again, it is assumed that, you can't have, if you do this, they didn't ask us to state any restrictions here, but x could not be 0, y could not be 0, otherwise you'd be dividing by 0. And if you look at the end here, y could also not be 1, but they didn't ask us to do this, even though this is correct if they asked for you to state restrictions. All right, same thing here, except now we've got to find common denominators for the numerator and the denominator. So if you look at the numerator, so I need to find common denominators. Now, one thing I want to caution you about is even though in equations we could just multiply everything by the common denominator, that totally works. You want to just be careful doing that in expressions, even though I'll show you a different strategy here in a second. But let's just do the common denominator strategy. The common denominator here is just x, so I can rewrite that. For the bottom, the common denominator is 2x. So give this guy the x, give this guy the 2's. I'm just multiplying by 1 on all of these, so that works out just. So when I simplify, I get this. And the reason I'm doing this, so the common denominators, is because now, not until you have just a single fraction, you can't have like a binomial, even though there's a binomial in a fraction, can you like apply the, actually divide those things. So the idea is that when you have everything kind of stuck together is when you can actually divide. So now I'll multiply by the reciprocal here. Notice how I flipped that bottom fraction. And then you just multiply across. If anything does cancel or reduce, you can do it from the jump. So it's like this x and this x cancel out, and that's about it. I could also factor this thing out right here. Like I can factor this as 3 times x minus 1 if I want to do that. But nothing else. Be careful. Again, don't try to reduce this 2 and this 2. You can't do that. So you could totally you can factor this out, and then the convenient thing about that is the 3 and the 2 then multiply to get a 6. So you get this as your final answer. If you want, this is acceptable. You could redistribute that 6. I don't recommend doing it. I'm not going to penalize you for it. But you could write your final answer this way. But again, if you write it this way, even though it's okay, it allows the reader to see that everything's reduced if you leave it in factored form. That's the reason why we prefer it that way. So I encourage you to just leave it in factored form, which part of that involves when you can factor something out that you do exactly that. That's it for part one of